For this example, we're going to be looking at this block P, which is initially at rest on a rough horizontal surface, and we have an applied force F, which is increasing in magnitude in a linear way with time, according to the curve that's shown there to the right. And what we want to do is to find out that as a result of this applied force F, what's the speed of the block when t is equal to 10 seconds. So since we're looking for change in speed for change in time, we'll use the linear impulse momentum equation. But of course, we need to first look at our FBD. What forces do we have acting on the block? Well, we have weight, we have the normal force N, we have the applied force F, and we have a friction force here. Since the block is going to be moving to the right, then the friction force will oppose that. So that's acting to the left. So in using our linear impulse momentum equation, first thing I'm going to do is sum forces in y. I'm going to use x and y like this. Sum forces in y, I got n minus mg. And since the block is moving along a horizontal surface for all time, the y component of acceleration is a 0, so N here is equal to mg, which is 100 pounds. What we're going to use in the linear impulse momentum equation is the summation of forces in x. That's the applied force F minus the friction force. And therefore, if we integrate that in time, that gives us the change in momentum for the block. So the m times v2 minus v1, it starts out from rest, so v1 is a 0. Well, we need to think a little bit, though, about how this friction force is going to change in time. What we know is that until the applied force F reaches mu sub s times n, that would be 0.5 times 100 or 50, the friction force is going to balance out the applied force. So in time, if I show this in blue, the friction force is going to be following the red line like this until we get up here to an applied force of mu s times n, which is 50 pounds. That will occur at 2.5 seconds. That's just based on looking at that straight line curve in the slope like that. At that point, the friction force then immediately drops down to mu sub k times n, 0.2 times 100, so that drops down to a 20. And then from there on out, friction force is a constant, again at mu sub k times n, which is 20 pounds. So what we see here is that up until what time I'm going to call T1, the block doesn't move because the friction force and applied force cancel each other out. So I can start the clock here at T1 because nothing happens before then to T2. Okay, so what I will do is integrate F from T1 to T2, and then integrate the friction force from T1 to T2, and that's equal to mv2. So this becomes just finding the area under the curve. The applied force F, its contribution, see if I can draw this in here, its contribution is going to be the area under this curve, like that. So that's going to be 1/2 the base, which is T2 minus T1, times the sum of the two sides. Recall the area under a trapezoid is 1/2 the base times the sum of the two sides. So the left-hand side is a 50. The right-hand side is 200. So that's the applied force. The friction force is just what we need to do is subtract away this part here. That's just a rectangle. So its area is going to be the height, which is 20 times T2 minus T1. And since that's equal to mv2, if I want to find v2, then I just divide the left-hand side here by the mass m. M would be 100 divided by 32.2, like that. And that's v2. So although the linear impulse momentum part here is a very straightforward application of that equation, that is, the impulse is equal to the change in momentum. In order to find the impulse, we have to think a little bit first about how this thing moves. And let's go back over that. The block cannot move until the applied force reaches mu sub s times n. That's 50 pounds. So all along here the force is increasing, but nothing occurs. And then at that time of 2.5 seconds, the friction force then drops down to mu sub k times n, and that's when we get the net force, which is bringing about the motion. We find the area under the applied force. That's this first part here, 1/2 T2 minus T1 times 50 plus 200, and then subtract away the impulse due to friction. That's this term here. Divide by m, and that gives us v2.